Have you ever just, stopped and wondered if there's a single blueprint for, well, for everything?
Like a fundamental operating system for the entire universe.
Exactly. From the absolute smallest quantum flicker right up to the grand scale of galaxies. It's a massive question.
It really is. And today we're going to dive deep into two incredibly ambitious ways physicists are trying to answer that.
We're looking at string theory, which many people have heard of, elegant but facing challenges.
And a newer, really expensive contender called the hypersymmetry, hypergravity, hyperfractal coherent resonance framework. Quite a mouthful.
HHHCR for short, maybe.
Definitely HHHCR.
Yeah.
Our mission today is basically to unpack what these theories are really saying.
Right. Look at the insights, the mysteries, and how HHHCR sort of tries to build on or maybe reconstruct string theory.
Mm-hmm. We want to pull out the key ideas so you can get a solid handle on them without, needing a PhD in theoretical physics.
Okay, let's start with string theory then. It's been a dominant force in theoretical physics for, decades now?
Oh, absolutely. Since the 80s, really, it's been central.
So standard physics, you think, points, right? Like tiny dots are the fundamental particles.
Correct. Point particles.
Yeah.
But string theory says, no, hold on. At the most fundamental level, everything is made of incredibly tiny one-dimensional loops or strands, strings.
And they're not just sitting there, they're vibrating.
Exactly. Vibrating. Think of like a violin string. Different vibrations give you different musical notes.
Oh.
Well, in string theory, different vibrational modes of these fundamental strings give you different particles.
Oh, I see. So one vibration pattern is a photon, another is an electron, another a quark.
Precisely. And crucially, one specific vibration corresponds to the graviton, the hypothetical particle that carries gravity.
And that's the huge ambition, right? To finally unify gravity, which Einstein described with general relativity.
With the other forces, which are described by quantum mechanics. Quantum gravity, the theory of everything. That's the goal.
So where did this idea even come from? It sounds pretty out there.
Well, it has roots back in the late 1960s. Gabriele Veneziano found this interesting mathematical formula describing the strong nuclear force.
Okay.
And then Susskind, Nielsen, and Nambu realized, hey, this math looks like it describes vibrating strings. Initially, it was about the strong force.
But then it grew.
Yeah, in the 70s, Schwartz and Shirk took a leap. They realized one of the notes, one of the vibrational modes, had the properties of the graviton. That's when it became a theory potentially unifying all forces, including gravity.
And figures like Witten and Green really pushed it forward in the 80s.
They did, leading to what's called the first superstring revolution. It became hugely prominent.
So let's recap the core assumptions. First, fundamental entities are strings, not points. Open or closed loops.
Yeah, and their vibration determines the particle type. Second, and this is where it gets really mind-bending for most people, extra dimensions.
Right, not just the 3 space dimensions plus time we experience.
No. String theory generally needs 10 or 11 space-time dimensions to work mathematically to be consistent.
So where are they? I see 7 extra dimensions around me.
The idea is they're compactified. Yeah. They're curled up incredibly tightly on unimaginably small scales.
Like smaller than an atom. Way smaller.
Oh, vastly smaller. Typically, the idea involves these complex 6-dimensional shapes called Calabi-Yau manifolds. The exact shape of these hidden dimensions is actually what determines the physics we see in our larger dimensions, the particle properties, the forces.
Wow. Okay. And then there's supersymmetry. Cis-U-N-Y.
Right. Supersymmetry, or cis-Y. It's a proposed symmetry between the two fundamental classes of particles. Fermions, which make up matter.
Like electrons and quarks.
Exactly. And bosons, which carry forces.
Like photons.
Cis-Y pairs them up. Every fermion has a hypothetical boson partner and vice versa. Mathematically, the symmetry is really important. It helps cancel out infinities and stabilize the theory.
And it's not just strings anymore, right? You mentioned brains.
That came later, particularly with M theory. Brains, short for membranes, are higher dimensional objects. A string is a one brain, but you can have 2 brains, membranes, 3 brains, and so on. They turn out to be crucial for understanding things like black holes and connecting different versions of string theory.
And interactions are governed by gauge symmetries, like in the standard model.
Yes, the interactions between strings, how they split and join, are described by gauge theories, leading to the force carriers, the gauge bosons.
It sounds incredibly complex mathematically.
It is, deeply rooted in very advanced math. Conformal field theory, Riemann surfaces, algebraic geometry, especially those Calabi-Yau manifolds for compactification. It's driven a lot of mathematical innovation, too.
You also mentioned dualities in M theory.
Yeah, this is fascinating. Dualities are like mathematical dictionaries. They show that two seemingly very different string theories, or even a string theory and a theory without strings, can actually be describing the exact same physics, just from a different perspective.
Like looking at the same object from different angles.
Kind of like that, yeah. T-duality, S-duality. These discoveries led physicists, particularly Edward Witten, to propose that the 5 consistent superstring theories were actually just different corners, different limits, of a single, more fundamental 11-dimensional theory.
And that's M theory.
That's M theory, though we still don't fully know what M theory is, fundamentally. It's more a framework that connects the known theories.
Okay, so what has string theory actually achieved, theoretically speaking?
Well, huge contributions. It provides a mathematically consistent way to treat gravity quantum mechanically. The graviton just pops out as a string vibration.
They're big.
Huge. It offers a framework for unifying all forces and particles. It's given profound insights into black holes, particularly explaining their entropy, their information content using D-branes.
Right.
It has implications for cosmology ideas about the very early universe, inflation, maybe explaining dark matter or dark energy. Even the multiverse concept comes partly out of the string landscape. And the ADA-SCFT correspondence.
That sounds technical.
It is, but it's a really powerful tool. It relates a string theory in a certain kind of space-time, anti-de Sitter space, to a quantum field theory on its boundary. It's like a hologram, a lower dimensional theory describing higher dimensional gravity. It's used to study problems in many areas now.
So the appeal is clear. It's mathematically beautiful, potentially unifying.
Elegant, consistent, where other theories fail on quantum gravity, provides insights.
Yeah?
Yeah.
But the hurdles. Let's talk about the downsides or the criticisms.
The biggest one, no question, is the lack of direct experimental evidence.
Because the strings are too small, the energies needed are too high.
Exactly. The predictions typically involve the Planck scale. Energy is about a quadrillion times higher than the Large Hadron Collider can reach. So we can't just, see a string.
Okay, that's a major problem for a scientific theory.
It is. Then there's the landscape problem, because there are so many ways to compactify those extra dimensions, maybe 10 to the 500 possible Calabi-Yau shapes or configurations.
10 with 500 zeros.
Something like that, yeah. An astronomical number. Each configuration could correspond to a different universe with different physical laws. So how do you find the one that describes our specific universe? It makes unique predictions incredibly difficult.
It sounds like it predicts everything, so it predicts nothing specific.
That's the criticism, yeah. It's hard to falsify. Related to that is the lack of uniqueness, multiple string theories, M theory, not fully formed.
And the reliance on supersymmetry.
Which hasn't shown up yet experimentally. The LHC has looked hard for supersymmetric particles and found nothing so far. If Suiswai is wrong, or only exists at much higher energies, it weakens a key pillar of most string models.
Plus, it's just incredibly complex math.
Very abstract, very hard for many physicists to work with, which can sometimes hinder progress or collaboration. And predictions often depend heavily on assumptions about that compactification process we can't test.
So powerful ideas, deep insights, but real challenges, especially on the experimental front.
Definitely. Which has led some physicists to feel it's maybe not the final answer, or at least not the whole answer, and that's prompted searches for alternatives or extensions.
Which brings us to this other framework, HHCR, hypersymmetry, hypergravity, hypofractal coherent resonance.
Right, and this is presented, at least in our sources, not as throwing string theory out, but as maybe absorbing and reconstructing its core ideas into something potentially broader.
Trying to address the gaps, maybe integrate some deeper principles.
That seems to be the idea. The core shift is away from just vibrating strings.
Okay, so what's the fundamental thing in HHCR?
It starts with something called coherent resonance nodal loci. Think of points of maximum stability or maximum resonance within some kind of fundamental coherence field.
So not a 1D string, but a stable point in a field.
Exactly. And these nodal loci, these resonant points, are what give rise to particles. Their properties, like mass and charge, aren't from vibration modes, but from their specific hyperresonance frequencies within this field. It's a shift from geometry to resonance and coherence.
Interesting. And what about dimensions? Still need extras.
Yes, but HHCR views them differently. Not as compactified spaces hidden away, but emerging naturally through a hyperfractal structure.
Fractal, like those repeating patterns.
Kind of, yeah. Imagine reality itself having a fractal structure, layers within layers of dimensionality. Each layer emerges through coherence dynamics. So instead of Calabi-Yau manifolds, you have dynamic fractal topologies. The compact dimensions are seen as fractal resonances woven into spacetime.
Okay, that's a very different picture. And supersymmetry.
That gets replaced by a broader concept, hypersymmetry.
Going beyond just pairing fermions and bosons.
Apparently, yes. Hypersymmetry is presented as a more fundamental principle unifying not just particles, but also their coherence interactions within this hyperfractal field. Particle behavior comes from things called hyperspinor interactions within higher dimensional coherent structures. It's meant to be a deeper form of symmetry.
What about brains?
They're reinterpreted as hyperfractal membranes, extending across these different fractal layers or dimensions.
And hypergravity, what's that?
This is key. Hypergravity is proposed as the force governing interactions between these fractal membranes and coherent nodal points. It's not just standard gravity, it's potentially much stronger at certain scales and dynamically connects everything. The sources even suggest it might be the exotic matter needed for things like wormholes or faster-than-light concepts by manipulating the fractal structure.
Wow, okay. And gauge symmetries, the forces?
They're also tied directly to coherence. HHHCR talks about a resonance operator and coherence conduit, linking gauge symmetries to the conditions needed for coherence. So forces emerge from the coherence properties of the hyperfractal structure. This could allow for new forces beyond the standard model associated with different fractal layers or symmetry reduction.
So it tries to extend M-theory's unification goal.
Yeah, by seeing the entire universe as this hyperdimensional hyperfractal continuum, M-theory and the string theories become aspects or layers within this larger coherence-based structure.
And those string dualities.
They become fractal symmetry transformations. Transformations between different fractal scales show how coherence conditions map onto each other. It's about the underlying symmetry of the fractal structure itself.
Even black holes are different.
Described as hyperfractal nodal points, areas of intense interaction between hypergravity and coherence, like coherent sinks, where information gets transformed and reordered through fractal processes. Not just information loss, but transformation.
Okay, so based on this description, what would be the key advantages HHHCR claims over string theory?
Well, first, putting coherence right at the foundation. Mass, forces, particles, all seen as emergent from coherent interactions, rather than starting with strings and seeing what comes out. It aims for a more integrated picture.
A sort of purposefulness built in.
You could potentially see it that way, yeah.
Yeah.
Second, the active fractal scaling for dimensions. It's presented as more dynamic and adaptable than the static compactification in string theory.
Less reliance on picking one specific Calabi-Yau shape out of gazillions.
Potentially, yes. Third, it claims to naturally integrate gravity via hypergravity and the coherent structure from the get-go, tackling that unification challenge head-on.
And broader symmetries might mean more predictive power.
That's the hope. More flexibility to explain observed phenomena and potentially predict new ones arising from different fractal layers or coherence levels.
Let's dig into some of the specific mechanisms proposed. How does it explain, say, the different generations of particles? We have the electron, then the heavier muon, then the even heavier tau.
Right. HHHCR suggests these emerge from different coherence thresholds in the field. The first generation, electron, up quark, down quark, represents the highest level of coherence, the most stable resonance, hence the lowest mass.
Okay.
The second generation, muon, charm, strange, represents a lower coherence threshold, making them heavier and less stable. The third, tau, top bottom, has even lower coherence, making them heavier still and very unstable. The idea is that below a certain coherence level, stable particle formation isn't possible.
That's a neat idea. What about particle decay? Usually we think of that as things falling apart.
This is one of the most counterintuitive twists in HHHCR, according to the source. Decay isn't breakdown, it's coherence enhancement.
Enhancement? How?
An unstable particle, like a muon, is in a state of lower coherence. It decays by realigning itself with the underlying hyperfractal structure, moving towards a more coherent state, like an electron, and shedding the excess mass energy as other particles, like neutrinos.
So decay actually increases the overall coherence.
That's the claim. And this contributes to what the framework calls negentropic processes. Instead of the universe just tending towards disorder, entropy, this coherence field actively drives processes towards greater order and complexity. Megentropy.
That's profound. A universe striving for order.
It's a very different cosmological picture than the standard heat-death scenario.
And mass and inertia. Not fundamental properties.
No. Emergent from coherence. Higher coherence with the hyperfractal field means lower mass. Inertia resistance to changes in motion is seen as resistance to changes in coherence alignment. So, highly coherent particles offer less resistance.
How does it handle the forces in symmetry breaking? Like how the electromagnetic force carrier photon is massless, but the weak force carriers, W and Z bosons, are heavy.
It links gauge symmetries directly to fractal layers of coherence. The standard model forces, strong, weak, electromagnetic, correspond to different layers. Symmetry breaking, where particles gain mass, is interpreted as a reduction in coherence for the force carriers.
So the W and Z bosons are less coherent than the photon.
In this picture, yes. They represent a state where the initial hypersymmetry related to the electroweak force has been broken, their coherence reduced, leading to them acquiring mass and the force becoming short range. The photon remains massless because the electromagnetic symmetry remains unbroken, representing a higher coherence state.
And new forces could emerge from other layers.
Potentially, yes, associated with higher-order symmetries or different coherence conditions unfolding. Force strengths could even vary slightly based on coherence modulations.
What about fundamental constants? Speed of light, Planck's constant, are they fixed?
HHCR suggests they emerge from the harmonic resonance of the whole hyperfractal field, like the fundamental frequency and overtones of the universe. This might even allow for very subtle variations over cosmic time or in different regions tied to the coherence field's state.
And particles are harmonic nodes.
Yeah, stable points of resonance within this field, not just simple vibrations.
And finally, compactification, curling up extra dimensions, is driven by hypergravity.
Yes, it's presented as a dynamic process of fractal symmetry reduction, with hypergravity acting as the agent that shapes these fractal dimensions, rather than just assuming a fixed geometric background like a Calabi-Yau manifold.
Okay, this is where the framework seems to go beyond typical physics. It starts integrating philosophical, almost metaphysical ideas.
Absolutely. Our source material indicates HHHCR explicitly incorporates concepts like consciousness, negentropy, and even refers to the divine into its structure.
How does symmetry breaking fit into that?
Yeah.
Usually it's just seen as a physical mechanism.
Here, it's reframed as a creative act, not just disruption, but the engine for complexity and diversity.
Explain it.
Hypersymmetry is seen as the original state of perfect unity, ultimate potential, almost like a divine state where nothing is differentiated.
Okay.
The breaking of this perfect symmetry is described as a creative explosion. It's what allows distinct forces, particles, dimensions to emerge, generating the creative multiplicity of the universe we see.
But not chaotic breaking.
No, the framework emphasizes its coherent symmetry breaking, guided by the coherence field itself, ensuring that complexity and order arise, not just randomness.
So particle creation is cosmic creativity.
That's the language used, yes. Mass generation, particle types, all consequences of specific coherence conditions during these creative symmetry-breaking events.
And even space and time emerge this way.
Presented as emergent properties. Time as the process of symmetry-breaking unfolding, space as the emergent geometry resulting from it. And this complexity is what allows for life and consciousness, which are described as coherent symmetry-broken systems.
And the philosophical angle. The divine.
The sources connect this creative process directly to a divine act or divine intelligence expressing itself. The universe's tendency to return towards coherence is seen as part of ongoing cycles of divine creation and realignment.
Let's touch on the math briefly. You don't need to give us equations, but how does it model this coherence field?
Okay, conceptually, there's a core equation for the coherence field. Let's call it C. Part of it describes how C propagates, like a wave. Another part describes how it interacts with itself non-linearly, driving the resonance. And a key part is a potential energy term.
Like a landscape the field rolls around in.
Exactly, often something like a Mexican hat potential. The field naturally wants to settle in the lowest energy state, the brim of the hat, not the peak. Falling from the peak, hypersymmetry, into the brim is the symmetry-breaking process, giving particles mass and distinguishing forces.
And the fractal dimensions.
Modeled using math that allows the dimension d to vary from point to point, and over time, linked to the strength of the coherence field C. So space-time's geometry itself is dynamic and depends on coherence.
And forces and mass are directly tied to C in the equations.
Yes, the equations for gauge fields, forces, explicitly include interaction terms with C, which is how force carriers can get mass when symmetry breaks. Particle mass m is literally defined as some function of C, and those generation thresholds are specific values of C.
What about the negentropy, the drive towards order?
The coherence field C is described as having harmonic oscillations, like waves. The frequency of these waves is linked to a negentropic potential, mathematically ensuring that higher coherence leads to states of greater order. There's an equation showing the rate of entropy change is negative when coherence is high.
So mathematically, higher coherence means lower entropy or increasing order.
That's the core idea, which underpins this concept of divine coherence as the foundation of physical law.
Meaning all other laws, Newton's, Maxwell's, Einstein's, are just approximations or consequences of this deeper law of coherence.
Essentially, yes. They're seen as describing how things behave under specific coherence conditions. Forces become tools of coherence, guiding systems towards alignment and balance.
And symmetry is divine harmony.
Reflecting the underlying coherence the universe strives for, symmetry breaking becomes a creative act within that harmony, not just random disruption.
How does quantum mechanics fit quantum coherence?
It's seen as a direct manifestation of this deeper principle and expression of divine interconnectedness. Quantum decoherence, where quantum effects seem to fade, is reframed as a realignment of the quantum system with the larger coherence field of its environment.
And entropy is a divine principle.
Driving systems toward organization, reflecting a divine intention for complexity. Life is seen as the prime example of this negentropic drive in action.
What about consciousness?
Proposed to arise universally from coherent interactions, it supports pan-consciousness, the idea that consciousness is fundamental. As systems become more coherent, they align more with the divine mind, the source of intelligence. Human consciousness is a reflection of that.
So the whole universe is evolving towards what? Higher coherence.
Yes, the large-scale structure, cosmic evolution, all governed by this law of coherence. The universe as a coherence machine, negentropically evolving towards greater order, complexity, and perhaps consciousness, not just fading out.
And human evolution fits into this.
Seen as part of this cosmic trend, aligning humanity with the divine coherence field, potentially allowing access to higher consciousness, making us participants or co-creators.
Okay, wow. That's a lot to take in. We've gone from tiny strings to cosmic coherence and divine intention.
It's definitely a journey through some ambitious ideas.
So just to recap, we started with string theory, mathematically elegant, aiming for unification, proposing strings and extra dimensions, but facing big challenges with experimental proof and the landscape problem.
Right. A beautiful framework, but maybe incomplete or needing modification.
Then we explored this HHHCR framework, which attempts to reconstruct those ideas around a central principle of coherence, using hyperfractals, hypersymmetry, hypergravity.
To build a picture where particles, forces, mass, even space and time emerge dynamically from coherent resonance within this fractal structure.
And it doesn't shy away from integrating concepts like negentropy, consciousness, and a guiding principle, suggesting a universe that's not random but purposeful and self-organizing towards complexity.
Offering potential conceptual answers to string theory's issues, but obviously itself a highly theoretical and currently untested framework.
Absolutely. It paints a very different picture of reality.
So the final thought to leave you with, perhaps. If the universe is, in some fundamental way, striving for higher coherence, for greater complexity and order,
And if the laws we observe are expressions of this deeper drive, maybe even a kind of divine law, as HHECR suggests.
what does that imply about our own place in it all? What's our role, our potential within this vast, evolving, coherent cosmic symphony?